For decades, aircraft wings were designed using a fragmented approach. Engineers calculated lift section by section, reinforced structures where stress appeared, and assumed that if each part worked, the whole wing would work as well. Yet aircraft continued to suffer from unexplained drag, uneven lift distribution, and structural inefficiencies that limited speed and range. The problem was not engines, it was not materials, it was not even the airfoil itself. Max Munk identified the real mistake. Engineers were designing wings without understanding how lift is distributed across the entire span. By treating the wing as a complete aerodynamic system rather than a collection of parts, he exposed why aircraft wasted performance and laid the foundation for modern wing engineering. By the early 1920s, aviation had moved beyond its experimental infancy, but aircraft performance was still governed by assumptions inherited from trial and error design. Engineers understood how to calculate lift for individual airfoil sections, how to reinforce wings against structural loads, and how to improve engines incrementally. Yet, despite these advances, aircraft continued to suffer from persistent inefficiencies. Wings produced uneven lift along their span, induced drag was higher than expected, and structural weight increased faster than performance gains. Designers responded by adding material, increasing power, or accepting limitations as unavoidable. What they did not fully understand was that the problem was not located in any single part of the wing. It was embedded in how the wing functioned as a complete aerodynamic system. At the time, most wing design methods treated the wing as a collection of independent two-dimensional airfoils extended across a span. Engineers calculated lift and drag locally, assuming that if each section performed well, the entire wing would perform well. This approach worked reasonably at low speeds and small scales, but it failed as aircraft grew larger, heavier, and faster. Induced drag created by the generation of lift itself was poorly understood in 3 dimensions. Engineers knew it existed, but they lacked a systematic way to predict or control it. As a result, wings were often structurally heavy, aerodynamically inefficient, and optimized through costly experimentation rather than theory. Max Munk entered aeronautics at precisely this moment of conceptual limitation. Born in Germany in 1890, Munk was trained as a mathematician and physicist before turning to aerodynamics. His background set him apart from many contemporaries who approached aircraft design primarily through empirical testing. In the early 1920s, Munk joined the National Advisory Committee for Aeronautics, NACA, in the United States, an organization created to provide fundamental aerodynamic understanding rather than incremental design tweaks. NACA's mission aligned with Munk's mindset: identify the governing principles behind aerodynamic behavior, not just its symptoms. Munk recognized that the prevailing wing design philosophy was fundamentally flawed. Wings do not generate lift uniformly across their span, and the airflow around a wing is inherently 3-dimensional. The presence of wingtips causes pressure differences to equalize through span-wise flow, generating vortices that increase induced drag. This drag was not a secondary effect, it was directly tied to how lift was distributed along the wing. Munk understood that controlling lift distribution was the key to reducing induced drag and improving efficiency, range, and structural performance. His central insight was that there exists an ideal lift distribution that minimizes induced drag for a given lift and wingspan. Through mathematical analysis, Munk demonstrated that an elliptical lift distribution produces the lowest possible induced drag. This was not a stylistic observation or a rule of thumb. It was a rigorously derived result rooted in fluid dynamics and vortex theory. The implication was profound. Induced drag was not an unavoidable penalty of lift, but a controllable outcome of wing geometry. From this insight emerged what became known as the elliptical wing theory, often referred to as Munk's wing theory. Munk showed that wing planform, twist, and airfoil variation could be designed deliberately to approximate the ideal lift distribution. Engineers no longer had to guess where drag losses were coming from. They could predict them, quantify them, and reduce them through geometry rather than brute force. This marked a decisive shift from component-level optimization to system-level aerodynamic design. Equally important was Munk's formulation of Prandtl-Munk lifting line theory, which extended Ludwig Prandtl's earlier work into a practical engineering framework. While Prandtl had established the theoretical basis of lifting line theory, Munk transformed it into a usable design tool. He introduced corrections, clarified assumptions, and demonstrated how the theory could be applied to real aircraft wings, rather than idealized mathematical constructs. This made it possible for engineers to calculate lift distribution, induced drag, and span efficiency before building a single prototype. The consequences for aircraft design were immediate and far-reaching. Wings could now be designed lighter because lift distribution could be controlled to reduce bending moments. Induced drag could be minimized without increasing wingspan, preserving structural and operational constraints. Aircraft could fly farther on the same fuel, climb more efficiently, and achieve higher performance without additional engine power. These gains were not incremental. They redefined what efficient flight looked like. Munk's work also changed how wind tunnel testing was used. Rather than relying solely on empirical measurements, engineers could now use wind tunnel data to validate theoretical predictions. Discrepancies between theory and experiment became sources of insight rather than confusion. Aerodynamics matured from an art informed by experience into a discipline governed by predictive models. Despite the importance of his contributions, Munk's work was not immediately embraced by all designers. Elliptical wings were difficult to manufacture, and approximating ideal lift distributions introduced design complexity. However, the underlying principle that induced drag is governed by lift distribution could not be ignored. Even when designers chose non-elliptical planforms, they did so with an understanding of the trade-offs involved. This alone represented a fundamental change in engineering culture. By the mid-1920s, Max Munk had permanently altered the way engineers thought about wings. He did not design famous aircraft or chase records. He provided the intellectual framework that made efficient wing design possible. Every later advance in wing optimization, tapered wings, twisted wings, high aspect ratio designs, rests on the foundation Munk established. Aircraft no longer had to accept drag as an unavoidable consequence of lift. They could shape lift itself. And once that realization took hold, wing engineering would never return to its earlier assumptions. The true importance of Max Munk's work became clear when aviation moved from empirical experimentation to systematic design. By the early 1920s, aircraft development was accelerating, but progress remained inefficient. Designers relied heavily on trial and error. Wind tunnel testing existed, but results were often interpreted intuitively rather than analytically. Aircraft wings were modified incrementally, without a clear framework linking shape to aerodynamic behavior across different flight regimes. Munk recognized that this approach could not scale. Aviation was becoming too complex for intuition alone. Wings were no longer simple lifting surfaces. They were interacting systems where pressure, distribution, circulation, induced drag, and lift efficiency were tightly coupled. Without a mathematical framework, designers were solving isolated problems while missing the underlying structure governing wing behavior. At NACA, Munk focused on the three-dimensional nature of wings. Classical aerodynamic theory treated wings as extensions of two-dimensional airfoils, corrected afterward with empirical factors. Munk challenged this assumption. He demonstrated that lift generation on a finite wing could not be understood by simply extrapolating two-dimensional airfoil data. The interaction between wing sections across the span fundamentally altered airflow behavior. This insight led to one of Munk's most significant contributions, the rigorous formulation of lifting line theory for practical engineering use. While the mathematical foundations had been explored theoretically in Europe, Munk translated them into tools usable by engineers designing real aircraft. He established relationships between wing planform, lift distribution, and induced drag that could be calculated rather than guessed. One of his key findings was that induced drag depended not just on total lift, but on how that lift was distributed along the wingspan. Certain lift distributions minimized induced drag, while others wasted energy, regardless of engine power. This meant that two aircraft producing the same lift could have very different efficiencies purely due to wing geometry. Munk showed that an approximately elliptical lift distribution produced the lowest induced drag for a given wingspan and lift requirement. This was not an aesthetic observation. It was a direct mathematical result derived from circulation theory. The implication was profound. Wing shape itself could be optimized to reduce drag without increasing power or structural weight. This shifted how engineers approached wing design. Instead of asking how much lift a wing could generate, they began asking how efficiently it generated that lift. Aspect, ratio, taper, and spanwise loading became central design variables. Wings were no longer shaped primarily for structural convenience or manufacturing simplicity. They were shaped to control airflow behavior across the entire span. Munk's work also clarified trade-offs. Wings optimized purely for minimum induced drag could introduce structural penalties or handling challenges. Longer spans reduced drag but increased bending moments. Highly tapered wings improved efficiency but complicated stall behavior. By quantifying these effects, Munk allowed engineers to make informed compromises rather than blind guesses. Another critical contribution was Munk's systematic treatment of interference effects. He demonstrated how wings interacted with fuselages, tail surfaces, and engine nacelles. Lift generated by one component altered airflow over others, changing overall performance. This meant aircraft could not be designed as collections of independent parts. They had to be analysed as integrated aerodynamic systems. This systems-level thinking aligned closely with NACA's mission. Rather than producing isolated performance improvements, Munk's work enabled predictable design. Aircraft behaviour could be estimated before prototypes flew. Design cycles shortened. Failures became less catastrophic and more informative. During the interwar period, these methods spread rapidly across US aircraft manufacturers. Engineers trained on NACA reports adopted Munk's formulations as standard practice. Wing planforms for military and civilian aircraft increasingly reflected calculated lift distributions rather than historical precedent. Performance improvements accumulated quietly, aircraft by aircraft. Importantly, Munk's influence extended beyond speed and efficiency. His methods improved stability and control. By understanding how lift varied along the span, designers could better predict roll behavior, stall progression, and control effectiveness. This reduced the likelihood of sudden, asymmetric stalls and loss of control at low speeds. When World War II approached, the aerodynamic foundations Munk helped establish were already embedded in American aircraft design culture. Fighters, bombers, and transports benefited from wings that produced lift more efficiently, predictably, and safely. These gains were not dramatic in isolation, but they compounded across fleets and missions. Max Munk did not design iconic aircraft. He did something more durable. He gave engineers a language to describe wings mathematically, allowing performance to be shaped deliberately rather than discovered accidentally. By turning airflow into equations engineers could use, he helped transform aviation from an experimental craft into a disciplined engineering system. In war and peace, aircraft flew farther, more efficiently, and more reliably, because wings were no longer treated as guesswork. They were treated as solvable problems. That transformation began not with a new engine or material, but with Max Munk's insistence that wings obey mathematics and that engineers should listen. Max Munk's influence on aviation did not peak during his years at NACA. It expanded through the generations of engineers who inherited the tools he helped formalize. By the time World War II began, American aircraft design had quietly shifted from intuition-driven experimentation to calculation-based optimization. This shift did not produce a single revolutionary aircraft. It produced an entire fleet that behaved more predictably, efficiently, and safely under demanding conditions. The most important aspect of Munk's legacy was not a specific formula, but a design philosophy. Wings were no longer treated as isolated lifting surfaces. They were understood as systems governed by circulation, pressure distribution, and interaction effects. This mindset allowed engineers to anticipate aerodynamic consequences before metal was cut, reducing development risk and accelerating iteration. During World War II, aircraft performance depended on more than raw power. Fighters needed long range, manageable stall behavior, and efficient crews. Bombers required predictable lift distribution to maintain stability under heavy load and damage. Transport aircraft needed safe handling across a wide range of weights and speeds. Munk's methods influenced all of these requirements indirectly by shaping how wings were designed across the industry. Elliptical and near-elliptical lift distributions became common design targets, not because they were fashionable, but because their aerodynamic efficiency was quantifiable. Wing taper ratios, span lengths, and aspect ratios were chosen with mathematical justification rather than convention. This improved fuel efficiency, reduced induced drag, and extended operational range, critical factors in a global conflict. Munk's work also influenced how engineers managed compromise. No wing could be optimized for every condition simultaneously. Structural limits, manufacturing constraints, and operational demands imposed trade-offs. By quantifying aerodynamic penalties, Munk enabled engineers to decide where compromises could be accepted and where they could not. This decision-making framework was essential in wartime production, where reliability mattered as much as peak performance. Beyond World War II, Munk's influence extended into the jet age. Although swept wings, transonic aerodynamics, and compressibility dominated post-war research, these developments did not replace lifting line theory. They built upon it. Span-wise lift control, induced drag estimation, and system-level interaction analysis remained foundational even as aircraft entered higher speed regimes. Engineers such as Richard T. Jones and Richard T. Whitcomb addressed new aerodynamic challenges, but they did so within a design culture shaped by Munk's insistence on mathematical rigor. Swept wings still required optimized lift distribution. Area-ruled fuselages still depended on predictable aerodynamic interactions. High-speed flight did not eliminate three-dimensional wing effects. It amplified their importance. Civil aviation benefited equally. As commercial aircraft grew larger and heavier, induced drag became a major driver of fuel consumption. Efficient wings were essential for economic viability. Munk's formulations continued to guide aspect ratio selection, wing taper, and span efficiency well into the age of jet airliners. Modern wing optimization software still reflects the principles he helped establish, even when designers are unaware of their origin. Another lasting contribution was educational. NACA reports based on Munk's work became standard references for engineers entering the aerospace field. These documents taught generations of designers to think in terms of airflow distribution rather than isolated performance metrics. The result was a shared engineering language that transcended individual companies and aircraft programs. Munk's legacy is unusual because it lacks a visible artifact. There is no aircraft silhouette uniquely associated with his name. No iconic prototype carries his signature. Instead, his work exists inside the equations, charts, and assumptions engineers use daily. This invisibility is not a weakness. It is evidence of complete integration. When an idea becomes infrastructure, it stops being recognized as innovation. Modern aircraft wings are designed with computational tools far more advanced than anything Munk could access. Yet the underlying questions remain the same. How is lift distributed? How much induced drag is generated? And how do components interact aerodynamically? These are Munk's questions, asked with newer tools. Max Munk did not change aviation by building faster airplanes. He changed it by ensuring that wings could be designed deliberately rather than discovered accidentally. He transformed aerodynamic design from an art informed by experience into an engineering discipline governed by calculation. Every efficient wing flying today carries his logic, even if his name is rarely spoken. That is the mark of foundational engineering. Not the invention of a machine, but the invention of a way of thinking that endures long after the inventor is forgotten.